Metrology is the infrastructure for manufacturing.
We are using advanced metrology to enhance the precision and automation of robotic machining systems.
When machines communicate, they use a mathematical language.
Optical metrology has the potential for dimensional quality control with an accuracy down to the atomic length scale and literally at the speed of light.
The Future Metrology Hub is ensuring that critical national manufacturing projects have world-leading academic research pipeline.
Metrology is the science of measurement. The Future Metrology Hub is one of 13 EPSRC future manufacturing hubs and focuses on the measurement of features related to physical manufacturing such as distance, form and surface characterization. With over 70 academic and industrial partners, the Hub is active across a wide variety of sectors and works with all types of organisations ranging from large global corporations through to small independent companies. Metrology is a key enabling technology essential to the modern world of high-value, high-precision technologies and products. Accuracy in manufacturing is a fundamental requirement. Sir Joseph Whitworth, a pioneer in the field of precision engineering and standardisation, famously said, "You can only make as well as you can measure." According to the National Physical Laboratory, traditional product verification processes typically account for 10 to 20% of finished product costs, representing over £15 billion per year in the UK alone, while over 60% of British standards involve measurement or testing. Based at the University of Huddersfield, the Hub brings together a consortium of world-leading researchers with spokes at the universities of Bath, Loughborough, Sheffield and the AMRC. The Hub is led by Professor Dame Jane Jiang.
The vision of the Hub is to create groundbreaking embedded metrology and universal metrology informatics, and apply these technologies across the smart manufacturing environment. Over the last 3.5 years, the team has been working together, developing fundamental science and technologies, and transforming early-stage outcomes into industry-ready solutions.
Researchers at the spoke universities bring specialist knowledge and expertise, working to create new sensors and technologies for gathering data, as well as developing the sophisticated methods for curating, interpreting and analysing it effectively.
The focus of research at the Sheffield Spoke is metrology informatics and its demonstration through case studies in partnership with the AMRC. The aim is to extract maximal information from product and in-process data from the multiple stages of manufacturing towards providing a health assessment of the parts being manufactured. We achieve this task by deploying sensor fusion and machine learning methods and make predictions on the dimensional and surface metrology parameters of the product. This can also be thought of as providing a virtual metrology measurement, and we use this in a new strategy being developed called inspection by exception. The key idea behind inspection by exception is that the time-consuming inspection stage is excluded to products that are predicted to categorically conform to or categorically violate the manufacturing tolerances. We believe this approach has the potential to increase efficiencies in metrology-driven manufacturing.
Artificial intelligence systems need the same kinds of knowledge as humans to understand and describe the manufacturing environment. To achieve this, the Hub has developed an advanced language that machines can read and interpret. We call this the category semantic language. Mathematics underpins the process of analysing and interpreting measurement data. Features such as linear distance are relatively simple, but as we move towards a more comprehensive measurement approach, the challenge becomes significantly more complex. Characterising freeform surfaces is particularly challenging and is a major focus of the Hub's work.
For smart manufacturing, a key requirement is that future sensors and instruments must be light, ultra-compact, high-speed, and robust, but with the same level of the accuracy as laboratory-based systems and at affordable cost. Optical sensors are well suited to meet this criteria.
Loughborough University and its spin-out companies have long been involved in developing and applying novel optical technology for industrial use. Electronic speckle pattern interferometry, fringe projection and laser vibrometry are three examples from the recent past. Our work within the Hub has two main strands. Firstly, we're developing ultra-high-speed 3D vision systems based on fringe projection. These can be used to provide real-time feedback to guide robots in high-precision assembly tasks. The second main strand is developing a form of LiDAR. Like radar, LiDAR measures absolute distance, but with the very short wavelength of light we're able to achieve very precise distance measurements of better than 1/10 of a micrometer. With the techniques we've developed, we can already acquire the data at a rate of 100,000 coordinates per second, which is almost 1,000 times faster than current state-of-the-art commercial systems. What we have here is our first prototype LiDAR, or frequency scanning interferometer, as it's sometimes called. This has allowed us to demonstrate the principle, to prove the excellent distance and time resolution figures I've already mentioned, and also to patent the invention. However, the prototype is clearly too big for an industrial setting. We've therefore been working with one of the other hubs, the Future Photonics Hub based within Southampton's Optoelectronics Research Centre, to implement the whole concept on a tiny photonic integrated circuit.
Our research on the EPSRC Future Metrology Hub has led to innovation in the use of advanced metrology to increase the precision and automation of robotic machining. We envisage robotic machining in, for example, aerospace manufacture, where large-scale components are required to be manufactured to within a few microns of machining error and precision. This would help to increase the production rates for the next generation of energy-efficient aircraft. The problem with using robots is that they are more flexible than people think, and unwanted motions can cause machining errors of the order of 100 or so microns. To achieve the required accuracy, we need to monitor the robot, and we do this with laser trackers and other sensors. And we use the feedback signals from this metrology network to excite a system of inertial actuators. And these compensate for the machining forces and unwanted motions of the robot. In doing so, we've managed to reduce machining errors by 90%. We're now taking the methodology forward with GKN Aerospace and implementing automation in its new Global Technology Centre.
The Future Metrology Hub is working with the high-value manufacturing catapults metrology teams and their industrial partners to ensure alignment and relevance of research. The Hub is engaged with numerous large OEMs as well as smaller businesses to ensure that the research is being carried through into the wider industrial landscape and solving challenges that business is facing. Projects such as Airbus's Wing of Tomorrow programme and the Tempest Future Fighter programme stand to benefit from the Hub's work and ensure that the UK continues to compete globally in the manufacturing space.
Overall, the Hub aims to deliver groundbreaking technologies which will lead to a step change in the UK manufacturing capability. We are always keen to grow our network of academic and industry partners. And for more information about the Hub, or to find out how you can work with us, please visit our website.